This presentation is delivered by the Stanford Center for Professional Development.
Good. Well, this is, we're supposed to all pretend it's Tuesday. I'll be in Washington, unfortunately. So today, I'll finish up and give a wrap-up on the Analytic Center cutting plane method. And then we'll move on to actually one of the, I think one of the coolest topics that really kind of finishes up this whole section of the class, and that's the ellipsoid method. So we'll look at this. But I'll try to make clear sort of what's useful and what's not. The Analytic Center cutting plane method is useful, period. When you have a problem that you need to solve where you really do only have access to something like a cutting plane or subgradient oracle, and for whatever reason, I mean, you have to look at those reasons very carefully. But if you have such a problem, this is an awfully good choice. And it's going to beat any subgradient type method very much. It's going to have this is going to have much more computation, obviously, per step, more storage, all sorts of stuff like that, compared to a subgradient method, which involves essentially zero computation and zero storage. But these things will just, they're way, 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 way better than subgradient methods. Okay, so here's the Analytic Center cutting plane method. You're given an initial polyhedron known to contain some target set, which might be feasible points, might be epsilon suboptimal points. That doesn't really matter what it is. You find the analytic center of the polyhedron, which is to say, more precisely, you find the analytic center of the linear inequalities that represent the polyhedron. And you query the cutting plane oracle at that point. If that point's in your target set, you quit. Otherwise, you append this new cutting plane to this set. Now, of course, what happens now is your point xk plus 1 is not in pk plus 1 by definition. Well, sorry, it might be in it. If it's a neutral cut, but it's on the boundary. And what you need to do now is sort of at the next step, you'll need to calculate the analytic center of that new set. And I think I won't go through this. There's a lot of different methods. Infeasible Stark-Newton method is the simplest one, maybe not the best, but we'll go on and just go to a problem, and I'll show how this works. So this is this problem we've looked at already several times. It's piecewise linear minimization. It's a problem with 20 variables, 100 terms, and an optimal value around 1. And let me add, just to make sure this is absolutely certain here and clear. If this problem if you just had to solve a problem like that, it goes without saying you would not use something like an analytic center. You'd just solve the LP. Let's bear in mind that every one of these iterations requires an effort, that's at least on the order of magnitude of simply solving this problem to 10 significant figures right off the bat by a barrier method. So your code from last quarter, your homework code, which shouldn't have been too many lines, will actually solve this problem very, very quickly. In fact, I don't know, anyone want to take a cut at how fast it would be? You have to minimize a piecewise linear function, 20 variables, 100 terms. It's going to be an LP when you add another variable. It's an LP with, I don't know, what is it, 121 variables and 100 constraints or something like that. So let's say it's 20 variables, 100 constraints. Dominating cost is going to be actually forming like A transpose HA, period. So forming a 20 by 20 matrix, which is actually a matrix, 100 by 20 matrix multiply or something like that. So that's 100 times 20 squared. And you're going to do maybe 20 steps. That's an interior point method. How fast would that be? Just order of magnitude. What do you think? Microsecond. Well, it's good. You're guessing sort of the right numbers now. You might be a little bit low, because actually when you get down into the 10 and 20 variables, the n cubed the various BLAS extrapolations start falling off. But based on BLAS extrapolation, well, I can tell you how I do it. It's 20 squared times 100, and the way I do it is I I think, 1,000 cubed. Yeah, let's just say a second. That's way more because a Cholesky factorization is I don't know, it's 0.18 seconds on my laptop. Okay, so it's not a big deal. And but something else like a matrix multiply might be half a second. Okay, so let's call it a second. Let's round up and say 1,000 cubed is a second. Let's see, you get a factor of 10 right here, right? Because we're doing 100. You get 10, and then you get 50 squared, 2,500. So 25,000 times faster than 1 second. Let's say it's 40 microseconds. And let's be generous and say you're going to do 20 of those steps. I think I did that. So 40 microseconds times 20. So the answer is a millisecond. So it wasn't a microsecond, but your answer was in the right spirit. Okay, I just want all this is just to point out this particular problem could be solved easily to very high accuracy in under 1 millisecond. So these are very good things to know, by the way. Very few people know this. I promise you, if you go around and ask people if you ask the authors of large and widely used packages, they have no idea how fast you can solve small problems.
Is this leaving all constraints? Is this leaving every time you make a cut? Is this leaving?
Yes. So in this example, this is leave all constraints. So it must be understood here that when you start, we probably had 40 constraints because we probably put a box around it or something. I'm sure we did that. So we probably put a box around it. This has 40 constraints, and in the classic ACCPM thing, how many constraints have you got over here? That's it, 240. So the number of actually the size of the problem solved over here is 6 times as big as the problem here. It's 240. Okay, so. We'll get to a bunch of this. We'll talk about it and to see how this works. Nice thing you see here is you don't see that horrible slowdown you see in a subgradient method where you kind of go like this and then kind of slow, get into this nice 1/k very slow convergence. What you do is you see something that looks much more like an interior point method, except that would not be 200 steps, it would be 20 or something like that. You see nice geometric linear convergence. Okay, now the previous one shows this is f of xk minus f star, and what this shows is the best of those. So this is probably what matters, because when you terminate the algorithm at any point, if you terminate the algorithm at each point, of course, what you're going to return is the best thing you've seen so far. These long things here correspond. Actually, what do they mean? What does a long horizontal? What does a segment mean in this picture? This is iteration number versus suboptimality. Your best one.
Trying to satisfy the constraints.
What's that?
Trying to.
No. This is we keep all constraints. So what does it mean?
Infeasible?
No, can't be infeasible, right? Because we just it's infeasible. We stop. But that can't happen for this piecewise linear minimization problem. So, no, what this means here is that your FK best has not changed. It means, in this case, that for 10 steps, you produced points that actually were worse than the best thing you've already seen. This is just underscoring the fact that this is a non-descent method. So a flat part means that some people might say you failed to make progress. At least you failed to make progress in terms of finding a point with a better objective value. Actually, how have you made progress? What actually did happen in one of these little steps?
You have a more constrained space.
Yeah. So your PK got smaller. So technically speaking, your ignorance was reduced over that step, but you failed to produce a point. You were lucky or whatever. You had a good point. But your ignorance, and that ignorance actually is going to translate into future, future good point values. It just hasn't. So that's what those mean. Okay. Now, if you want to compare this to sort of Newton steps, I think if we go back and forth, we can look at the two pictures. That's 200 iterations, and here you can see we did about, I don't know, what's that? About 10. It's about 10 11 Newton, 12 Newton steps, something, about 11 Newton steps average per, so it took on average about 11 Newton steps to recalculate a new analytic center. By the way, I should mention this is not tuned. We probably had I think we did have a fairly small tolerance for analytic centering. In other words, we probably calculate the analytic center to lambda squared is less than 1 e minus 6 or something like that. Needless to say, that means that the last 3 Newton steps we took in every one of our centerings was a complete waste of time. Because remember, the goal here is not to calculate the analytic center. The goal is to get a good enough query point so these numbers, you could probably get it down to 5 Newton steps. I'm just saying if you actually wanted to do this. So this is just sort of straight out of the box. No, well, all the code's online, so you can look at it as well as I can.
For the infeasible Newton step, don't you have to wait until you get feasibility?
Yeah, yeah. And in fact, we don't have that here, but I might actually go back in the code and actually get some of the statistics, like how many steps on average to feasibility, precisely. Right, that would be a really good thing to know. So I think I may go back and do that. It'd be fun. You can, by the way, since the code's all there. Yeah, so that would be one question. And you can see, by the way, a little bit of curvature means that as this thing progresses, the centerings are getting a little bit harder. They're sort of, you're on a pretty steep thing like this for a while, and then the slope here is, well, half is. If you compare the beginning and the end, the centerings have gotten harder. By the way, what's the effort per Newton step? Is this a valid, does this track time well? Is that, that's Newton step. Does it track time? Is that a valid, so how does time grow with these?
So you're adding
one?
You're adding an extra constraint.
Absolutely.
Every
Right.
time. So yeah, I think
Okay. So it's growing linearly. The problem size. What's the computational complexity of the Newton step as a function of the number of inequalities? It's what? You guys have to get good at this. Here, you want to know you want to hear the sloppy way to do it? Someone just walks up to you on the street and says, "Quick, what's the complexity?" The big number times the small number squared, because that's the answer for least squares and any problem like that, right? By the way, that's conditioned on the fact that you've done it right. so if in fact if the big number squared times a small number, then it's wrong. But so that's my quick rule of thumb. Then later, when you can go catch your breath or whatever, you can go work out the the Newton step, and there's 20 of these, and it's forming that. But that's just a good working number. Just if m is bigger than n, it's mn squared. That's the answer for Newton for least squares as well, by the way. Least squares, least norm, everything. So, okay. So, therefore, the cost per Newton step, what's happening is you have like 20 variables. That's a small dimension. And then you have the big dimension is the number of constraints. And it starts at 40, ends at, I don't know, 240, what do we say? Something like, goes up by a factor of 6. And roughly speaking, it's growing linearly. So as you go along here, well, it starts at 40. That's a 6 times bigger problem in terms of the big dimension. Therefore, if you do things right, it's big dimension linear, quadratic in the small dimension, the cost of a Newton step from here to here actually goes up by a factor of 6 linearly. So what you would do is you'd have to do a quadratic distortion of this axis to give you the actual time. Make sense? Right, because each step over here costs 6 times what a step over here costs. A step in the middle costs 3 times. So all I would do is take these numbers and spread them out quadratically. I'd have an affine expansion. Make everybody cool on this? So that would be time. We didn't have it here, but it doesn't matter. Okay. All right. All right. So this just shows you again. This is just the absolute. This is the baseline. Nothing funny. No constraint dropping. No nothing. Just basic ACCPM right out of the box. So here what we've done is we've plotted 2 things. This is the true optimality. Now, of course, when you're running, you do not know this. You do not know this thing, right? We obtained this by, using CVX to solve this in, let's say not 1 millisecond, let's say on CVX, yeah, this interpreted overhead is gonna swamp everything. But you know, I guess by the time it gets down to SDBT3, it's probably 30 milliseconds. Wait, super fast. We got the actual solution, and then use that to judge our progress. This, however, so this you do not know in real time. What you do know is that this number. This is the best. This is the best upper bound. By the way, the lower bound is also does not go up monotonically, right? In an interior point method, right? What happens is at every step, you know, when you do a centering, you get a better point, so your objective value goes down, and not only that, your dual value goes up. So you get the beautiful things where your best point and you don't distinguish between your best point and your current point because it's always your current point is always the best one. It's a descent method, but your lower bounds also go up. So you have no logic in an interior point barrier method or whatever that says keep a hold of the last point because it may be a while before you see one that's better. Or in terms of lower bounds, you don't keep track of the best lower bound you've seen because the next 15 you might see are actually worse than the one you have. So here though you do know this one. And you can see it's off by some factor. I don't know. Let's see. It's a factor of 8 or something like that or whatever. So that's all. Just saying that's what this is. So your stopping criterion might be based on the red dash thing. Although I should probably say something. The subgradient method has, in general, I think it's fair to say from a practical point of view, no stopping criterion. So, but usually when you're running subgradient methods, it's in some situation where you're so desperate to have anything that does anything that you're just happy to have something. If things get better after 50 steps or 10, you know, that's good enough, right? So stopping criterion is a luxury that you, generally speaking, don't have when you actually apply one of these. The same might be true here in these, maybe less so, but still you have the same thing. Okay, now we do constraint dropping. All right, so here what we did is we, now by the way, keeping 3n is actually quite interesting because we start with 40 constraints. We start with a box on x. X is an R20. We put it in a box. I'm guessing that, but actually one of you with a laptop could actually look at the code and find out. You have a laptop. You don't have to. You don't have to do it. But I presume that's the how we initialize it with 40 constraints, which are box constraints. And this is the progress if you do no constraint dropping, the blue thing. And now remember, when you do no dropping up here, your polyhedron has 240 or whatever it is. Wait a minute. Yeah, up here. That's got 240 inequalities. So that's this thing in R20, polyhedron in R20, kind of a small one, by the way, at this point. It's quite small. And it's got 240 inequalities. By the way, I have no idea how many of the 240 are redundant. I presume the original 40 are redundant. The original 40 were the boxes, and the idea is we just made a big old box. So it would kind of be bad if those were still active. So those 40 are probably redundant. Probably a lot are redundant. But I don't know. We didn't do that calculation. But we keep 3n. So we're going to keep 60 at any given time. So by the way, a polyhedron in R20, what's the minimum number of inequalities that would define, that would give you a bounded polyhedron in R20? What?
40?
40 will in R20. Yeah, 40 would do it, absolutely. You could give a box, but that's not the minimum number. What's the minimum number? Can you do it with 8?
No.
What? Someone said no. Why not?
It's
Well, if you have 8 linear,
at least 20.
so you need at least 20. And if you have 8, then basically there's a 12-dimensional subspace of things orthogonal to those. And so you're unbounded just instantly in at least 12 dimensions. So you're not going to be bounded. So the answer is 21. You need 21. And a simplex is the smallest number of, it's the simplest polyhedron that's bounded. Simplest in terms of number of inequalities. And it requires n plus 1. So the point is it takes 21 inequalities to just have a bounded polyhedron. We're taking like 60. So it's not like it's a super, this is not an exquisitely detailed description of a polyhedron. And the wild thing here is you see this is just totally insane. The progress is identical. By the way, what roughly is the change in computation time? Again, not that we would care, but let's figure that out. What's the difference between computing the analytic center for the red guy and the blue? What is it there?
Cost for each Newton step.
It's what?
Cost for each Newton step.
Yeah, I know that, but I want to know the number. You can figure it out. Everything is here. You know all the dimensions. So, I mean, I want the number. Of course, the cost per Newton step is different. That's what it is. Now I want the number.
When you drop or when you don't drop?
Both. The blue is no drop. The red is keep 60. So you're dropping it.
Just
What is it?
240 minus 6, no,
240 over 60.
Yeah.
So in this case, you analytic center 240 inequalities, 20 variables. In the red case, you analytic center 20 variables, 60 inequalities. So again, big times small squared. It's linear and big. 240 versus 60, 4 to 1. Okay,
What about the complexity of reducing the redundant constraints?
Oh, that would be solving like an LP per step. Oh, now we could have we could do much more analysis in here that would sort of be fun. So you know an analytic center cutting plane method. At each step, you get for free some constraints you can promise, you can actually guarantee are redundant and drop them with no further discussion. You don't have to avoid your complexity theorist friends or anything like that. No, everything's cool because they're provably redundant. Actually, I would love to have figured out how many. At each step we dropped things, obviously. Well, actually, we didn't drop things until here, right? Because we started with 40, then 41, 42, 43. When we got to 60, we started dropping, and then it looked like that, right? That would be a plot of the number of inequalities, okay? So we didn't have to actually we didn't have to look the other way, at least for the first 20 steps. After that, when we start dropping, then the question is what fraction of the things we dropped were provably or actually redundant. All of those could be calculated by just solving some LPs, and those would be actually really good numbers to have. We should actually have them in here. It'd be fun. But it is very unlikely that everything we dropped. Oh, would that be right? Oh, hang on. No, that's not true. Sorry, I was about to say something that was wrong. Good thing I didn't say it. All right. Okay, but after all this discussion, though, let me make sure the big picture points are clear. So the big picture points are the following. First of all, it obviously works just as well. You do not need the number. You don't need there's no particular advantage in convergence are you getting by keeping all these constraints. That by limiting it to 3n, you're getting the full power. You're getting perfectly good convergence. The computational complexity, like that, means that the cost per step here is actually, in one case it's growing, and in another case it's just flat fixed. So that's the main point. By the way, proofs of convergence that handle constraint dropping are quite complicated, as you might imagine. They're quite complicated. So they exist. I'm very happy somebody's done it, so that I can tell you that somebody's done it. There's a gap in between. I might add there's a gap. I'm pretty sure there's a gap in between the things people do and the things people have proved converge. So I do not know if a method that keeping 3n is actually provably convergence. I actually don't know that. Maybe it is, maybe it isn't. But I've seen ones where you drop things, and these are quite complicated, as you might imagine. So, okay. Oh, I guess we figured this out on our own already, so there's nothing to say about this. This is sort of number of steps and the number of inequalities. I mean, it's kind of a silly plot, I think, right? But anyway, it's all right. Good. That's fine. Okay. So now we get to something interesting. This is using a megaflop counter in MATLAB, which is notoriously bad and all that. And I think people don't even use it anymore, but it doesn't matter. Just to get a rough idea, we should be able to figure out. Actually, we should be able to guess a lot of these things really, really well. So let's guess. Actually, I'll tell you how we can guess this plot. Let's go to the end and ask how much. What's the accumulated? We already decided. The red thing at this point is 6 times more efficient than the blue. That's what we decided, right? 4. Okay, sure, 4, whatever. Fine. Yeah, 4. Okay, so it's 4 times, And then how much faster is it in the middle? Ooh, I don't know. That's it's 60 versus 40 plus 100. 140? Close to 2. Okay, ready? These are street fighting methods. This is just quick, dirty methods, fast. If it's 4 times more efficient here and it's 2 here, what's sort of the average in efficient? And it kind of grows linearly or something. What's the average sort of advantage? 2, I don't know. What do you think? Well, it's not 8, okay, and it's not 4, and it's not 1. It's like, let's call it 2 to 1, and let's see if our prediction's pretty good. And our prediction is, oh, hey, what do you know? It took about 150 megaflops, and this took about 70. So that's the picture. So this shows that that constraint dropping, if you care about time or whatever, works this way. By the way, a lot of this doesn't matter so much because you usually use analytic center cutting plane in a situation where the oracle calls, the subgradient calls, are very expensive. I mean, for example, the oracle calls in most of the interesting cases, this is when you're doing distributed optimization, and the oracle call. I mean, these are like other computers, like on the other side of the world, doing all sorts of stuff is happening, and so all the analytic center cutting plane stuff is just like 0. I mean, even for a problem with 10,000 variables or something, that's how these things work. Okay. Now, if you do the epigraph analytic center cutting plane method, so now you have 20 variables and 100 terms, and what happens is you divide roughly I think this actually goes way down here. So you actually are dividing the number of steps required by just a factor of 4 or something, and that's it. I mean, I don't think I'm showing F best here, am I? Yeah, there we go. So this is the epigraph one, and here's what it looks like versus Newton steps, and I don't know what happens here, but I mean, it looks like you're doing pretty. There's points here where you're doing better or something, and the word on the streets, as I know it, is that you should is that the epigraph method is better. I don't understand it, to be honest. I'm not quite sure why, but anyway, that's for whatever it's worth. Okay, so this finishes up analytic center cutting plane method, and by the way, I should say that we haven't really. We actually haven't really seen yet the really cool examples where you would want to use these methods. And I admit that that's going to be the next chunk of the class, and we'll see some very, very cool applications where you really, really would want to use these methods. So, in fact, you will. So, okay. So the next topic is absolutely just beautiful. It's, you can guess where it's from.
Moscow.
You're right. Actually, Moscow and Kiev. It's from Yudin, Nemirovsky, Shor in Kiev, and so on. So, and guess when?
60s.
Close. Actually, it probably is 60s. They say, yeah, definitely, for sure, early 70s, and yeah, I'm sure they knew it in Moscow in the 70s or some 60s. Okay. So it's the ellipsoid method. Absolutely beautiful. By the way, it's quite famous too. It was not very well known in the West until maybe, I think certainly by the late 70s it was. Actually, in the late 70s it was on the cover of the New York Times front page. So because it was one of the first methods used to show that linear programs could be solved in polynomial time. Right. Oh, by the way, with a little star, meaning you have to go read the fine print. But then that was 1979. Then they had a hilarious article on the front page that basically said, that it was really funny actually, because it said linear programming runs the entire world, everything. All airlines are scheduled for it. Nuclear weapons are built by. I mean, just went on and on and on. And it said this is going to totally change your life because now. Oh, and by the way, I should add, at that point, for 30 years, people had been solving linear programs unbelievably well using the simplex method. just so you know. I mean, just amazingly well, right? So it's a non-issue. Anyway, but they called some mathematician, actually Rutgers, actually the poor guy who wrote the article. All he said was it was a complexity theory result, and it was a pretty good one. By the way, up until that point, people didn't know what the complexity of linear of solving linear program was, and they actually introduced a new class called LP, as in P. So you'd actually say, oh, this is class LP, and that meant it was as easy to solve as an LP, and vice versa. If if you had a method for solving an LP, you could actually solve these things. You had the two-way reduction. So no, they really did, and then it turned out P equals LP or something. You know, I mean, what I'm saying, if you really look into these things, you'll find out it's much more complicated and all that. And actually, some of the things I'm saying, if interpreted literally, are just wrong. But you know, this is roughly the idea. Okay, so anyway, this is on the front page of the New York Times, saying it was going to change the world, and it didn't. By the way, linear programming was on the front page again in 1984. So we'll get to that for barrier methods. Okay. This is just absolutely beautiful, this method. So this is the one I just talked about, is Katian, who by this time was at Rutgers, uses to show polynomial solvability of LPs. So actually, you're going to see a code now. So actually, what's funny about this is the subgradient method is to solve an LP. I think maybe you wrote it's not hard to write a 6-line code for it. And a subgradient method. So you can just write a subgradient method, solves any LP. Even more, if someone says, that's ridiculous. It's hard to write an LP solver. These are big, giant pieces of software. You have to know a lot. The proof is like a paragraph, right? Because it's the paragraph from subgradient method. Okay, so that's pretty cool. Slower than anything, right? But it is still nevertheless, it is cool that a 6-line program with a 2-paragraph proof solves any LP. Okay, this was going to be 8 lines. But even scarier, according to the complexity theorists, this is actually an efficient method. So, and the proof is quite short, which is even more shocking. But anyway, okay. Now each step is going to require cutting plane or subgradient evaluation. So it's the same as everything else. You're going to have modest storage, which is to say it's going to be O of n squared. Which, by the way, is if you do analytic center cutting plane method with dropping, the storage is n squared. Because you have n variables and you store, let's say, 3n, 5n constraints. That's all you need. The only state in that algorithm is the polyhedron. So your storage then is like whatever, 6n squared. That's it. And your update cost, by the way, is n cubed in that one, obviously, because it's n squared, whatever it is. It's the big times the small squared. You can actually make it faster with low rank updates, but that's another story. Okay, so it's got modest storage. In the ellipsoid method, the update will involve solving you will solve a convex problem, but it has an analytic solution. And it's going to be order n squared. And it's efficient in theory, and it's slow in practice, but it's actually something like, it's like the subgradient method, actually. Except that it's better than the subgradient method. It's kind of slow in practice, but it is way robust. I mean, it sort of, you can blow off whole parts of it and start it in the wrong place, initialize it wrong, and it's going to be, you can give it like totally wrong subgradients, many, many times. It'll just very happily lumber along and work really well. So that's, okay. So the motivation goes something like this. In a cutting plane method, you need serious computation. I mean, I don't know. Do you really believe that? I mean, it's 10 Newton steps. Each Newton step is a least squares problem. So, okay, so it's 10 lines. But, this scares people. And people make a big deal about, an analytical formula, like a Kalman filter update versus, if there's a conditional or a line search, they get all weird about it. Of course, that's completely stupid and idiotic if you think about it, right? Because a Newton step is nothing but a least squares, So I don't know why people... I mean, it's fine to have an analytical formula, and that's all great and everything. But the idea that these are like sharply divided is really, really dumb, I think, in my opinion. It's a distinction that actually makes absolutely no sense. What only matters is how fast can you carry out that calculation, number one, and what is the variance in that calculation. And nothing else, nothing whatsoever else matters. Okay, and the variance can range from 0, if you're doing like a matrix multiply, right? to, you know, a little tiny bit of, if you're doing a sparse matrix factorization, considerable. I mean, it depends on the, with a not given structure, you have huge variance because it depends on who did the ordering for you and how much fill-in you get and all that kind of stuff. To an eigenvalue calculation, for a dense matrix, it has a very small, it's order n cubed, but it has an n squared component that, or an order n component that actually is subject to some variation, which is the number of steps required to calculate the eigenvalues. Obviously, if it's n cubed plus a random number times n, we have the way to summarize that is it has no variance. Right, so, okay. All right. Okay. Oh, we just talked about this at great length. The other issue is this, is that the localization polyhedron grows in complexity as the algorithm progresses. We already talked about that. Now, I have to say, if you keep it proportional to n, like this, then, so this second bullet is not a problem in practice. This is if you make a practical, if you do analytic center cutting plane method, you are going to prune constraints. Okay, that's the way it's going to. That's how they're done in practice. That's how they work. They appear to work just fine. In which case, this is not an issue. So this only irritates maybe your aesthetic side or your theoretical side or something like that. So that's all that is. But now, ellipsoid method is going to address both. It's going to have a constant data structure, size data structure, to summarize your ignorance at each step. Analytic center cutting plane method has a variable size because it's a polyhedron with a variable number of constraints. And in the no cutting method, you just keep it grows. So, okay. So here's the ellipsoid method. The idea is this: you're gonna localize the point you're looking for in an ellipsoid instead of a polyhedron. Now, by the way, that's actually kind of a very cool idea right there. And ellipsoid actually is, has, in fact, what's required to describe an ellipsoid? What's the size of the data structure in Rn? What do you have to describe an ellipsoid? There's lots of different ways to do it, but what is it? What do you need?
Matrix and a vector?
Matrix and a vector. And a matrix is, n squared over 2. And a vector is like n. So, in fact, the matrix is really like n plus 1 over 2. It's n squared over 2. That's the answer. So the number, to describe an ellipsoid, a data structure for an ellipsoid requires about n squared over 2 elements. Let's see, let me ask a couple more questions. Oh, and an ellipsoid is an interesting set. They're very widely used in Rn. For example, if you do statistics or anything like that, it's sort of the first thing that kind of gives you that tells you about direction. So actually, let's just talk about localization sets just for a minute. Here's one, bounding box. So you have a box. Someone says to you, you're doing a calculation or you're doing navigation, and you say, okay, and someone says, how accurate are you? You'd say, well, give me, you'd want plus minus, 2 meters east-west, plus minus north-south, and elevation such and such, plus minus 8 meters or something. That's a bounding box, widely used. How big is the data structure required to describe a bounding box? In Rn. It's 2n. It's an L vector and a U vector. That's it. So that's 2n. Okay. So these are at the simple methods, right? Here's an even simpler one. How about just a ball? What do you need? It's not that simple. What do you need to describe a ball?
1. N plus 1.
N plus 1. You have to give the center and radius. So it's n plus 1. Okay. So these are order n data structures that describe geometric sets. And you can imagine, and they have uses. They have plenty of uses. Actually, for most people, this is the simple. They shouldn't be made fun of, these measures. They're extremely useful when someone says, how are you estimating the velocity of that vehicle? And you can say plus minus 0.1 meters per second. Everybody understands that. Makes total sense. Okay. Now, an ellipsoid is already the first sophisticated thing. You see it in sort of statistics because you talk about confidence ellipsoids. And what it captures is, in statistics, correlations. So, it allows you to capture the idea that you could know x plus minus a meter, y plus minus a meter. But for some weird reason, you know x plus y, to 10 centimeters. That's this kind of ellipsoid, right? So that's what an ellipsoid that's what an ellipsoid gives you. So you're into the n squared things. How about a simplex? Just for fun. Just roughly how many? What's the data structure? What's the size? What do you to give a simplex? N? Not a unit simplex, a general simplex. Convex hull of n plus 1 points. I just gave it away.
Is it can be n with 1 times n, or?
Yeah, it's n squared, roughly. I mean, actually, then it turns out you have to adjust for that because they're symmetric. But roughly speaking, it's order n squared. So actually it's a big jump when you go from an order n to an order n squared data structure described geometric set. You actually go from not the inability to universally approximate to ability to universally approximate. Universally approximate means I give you any old convex set, and you give me an approximation of whatever data structure you choose that has some bound that says, like, if you give an outer one, if you shrink it, it lies inside. Okay? Ellipsoids, bounding boxes do not do that because you make a little razor thin thing that goes at a 45-degree angle, and you're in big trouble because that bounding box is huge, and you have to shrink it infinitely far before it fits inside. But an ellipsoid, you have a bound. We did it last, or we saw it's like square root n or whatever. N is the factor for an ellipsoid. Square root n if it's symmetric. Okay, let's go on. It's just an aside. Okay, so here's what's going to happen. You know, the idea is you have an ellipsoid that summarizes your ignorance. You know the optimal point is in a current ellipsoid. Now, the nice thing about an ellipsoid is there's no long discussion about centers. It's sort of like it's like an interval, an ellipsoid. So, you know, you could say, well, let's calculate the analytic center of the ellipsoid. Let's calculate the CG. Let's calculate, you know, whatever you want. They're all the same. In fact, if you have a center of an ellipsoid and it's not the center, then I'm deeply suspicious of your definition of center. So the point is there's no real discussion there. There's just the center of an ellipsoid. And you evaluate a subgradient at that point. And what you do, that tells you instantly you have a cutting plane. So what's happened is you now know that your optimal point, you're in an ellipsoid, you have sliced off a half plane, and now you have, in the worst case, a half ellipsoid. And now you know. Now, if you did a standard cutting plane method, you'd calculate. Now, by the way, you have a half ellipsoid, and you start talking about, let's talk about the center. Now the centers vary. There's an analytic center, there's a CG, blah. And then you do it 2 steps, and you have now a set which is an ellipsoid sliced by 2 planes. And it, you know, that's so. In fact, there's another step that goes like this, and this is the main point. Here's what you do: you have a half ellipsoid, and in order to preserve constancy of the data structure, you're now going to do something that's equivalent to constraint dropping or whatever. You're going to set EK plus 1 be the minimum volume ellipsoid that covers your half ellipsoid. Okay? So step 4, step 3 is where you get your knowledge, your ignorance decrease. So this is ignorance decrease. And in fact, by the way, how much does the volume go down between EK and this localization set?
Factor of 2, right?
Yeah, factor of 2. If it's a neutral cut, if it's a deep cut, it's more than a factor of 2. So in step 3, you get at least 1 bit. In other words, log 2 of the volume. Log 2 of the volume of the localization set in step 3 goes down by at least 1. The worst thing that can happen is your ellipsoid is cut in half. No matter how you cut an ellipsoid, every plane going through the center of an ellipsoid cuts the volume exactly in half. Your volume goes down by exactly half here. Now, in step 4, your volume goes up. So 4 is actually an ignorance increasing step. And then there's just a big drum roll to find out whether or not here the ignorance increase in step 4 is more or less than the ignorance decrease in step 3. And that's basically the method. Yeah?
How are we finding that a minimum volume ellipsoid? Are we keeping track of half planes or?
No, I'm going to show you. There's going to be just a formula for it. Yeah, worked out by some Russians. Yeah, no, it's the basic one is simple, but actually they did things like 2 cuts and they actually had formulas for deep cuts and parallel cuts and crazy things. And then you get into some, there's actually analytical formulas for those. And those are formulas I believe only a Russian person would work out, I believe. But there are formulas for them. But this one's going to be simple. And I think you're going to work it out, because we're going to stick it on the homework. Do we have a, don't we have an exercise on that? We just calculate the minimum volume ellipsoid that covers a half ellipsoid?
Oh, no, we have a problem on that.
Oh, we do? Okay. But not yet assigned?
No.
How convenient. What do you know? Okay. So here's the picture. Picture goes like this. Here is your ignorance at the kth step. Now, by the way, some points in this thing could not be optimal, because remember, you're cycling between steps that decrease ignorance and then increase it. So first you decrease ignorance. You call, you get this is a neutral cut like this. And basically, this half ellipsoid, we do not have to look in ever again. So actually, at this half step, we can say that the solution lies in this half ellipsoid. Okay? And our ignorance just went down, in this case, by exactly 1 bit. Okay? Now the next step is we calculate the minimum volume ellipsoid that covers it. We're going to get an analytic formula for that. But the point is, here it is. It's this thing. And what's cool about it is things like this and this are very interesting. That's just slop. We have now, before this step, we know the solution cannot be in this little thing here. It cannot be there. And yet, we're going to include it in our localization step as we move forward. Okay? So that's the bad part. That's the slop. Yeah. Okay. So, all right, now compared to a cutting plane method, you could say various things like localization set doesn't grow more complicated. It's easy to compute a query point. Well, yeah, because it's actually part of the data structure of the ellipsoid, right? The ellipsoid is given by a point, the center, and some positive definite matrix. So, okay, fine. It's an access into a field of a data structure. Okay. The bad part is, of course, we're adding unnecessary points in step 4. I mean, these. Anyway, I wouldn't be here telling you about this if it didn't actually work. We'll get to that. So the first thing is the ellipsoid method in R reduces to bisection. Good. Very good. So in R, what's an ellipsoid in R? It's an interval. And then it says go to the center of that interval and get a subgradient. It basically tells you the left or the right is your new localization set. And indeed, you've gone down by 1 bit exactly. And now you have an interval, and you call a method that says, please find for me the smallest volume, in this case length, the smallest length interval that covers this interval. So I can write that method. That's easy. And in fact, in that case, there's no slop. But this example back I just showed, the visual example shows immediately. In R2, there's slop. That this is not, you are adding points into your localization set that you know for sure cannot be optimal. So there's slop. Okay. So we'll get to the formula, the update formula. That's easy. Now it turns out that the new localization set can actually be larger than this in diameter, but it's always smaller in volume. So this is how the drum roll ends. And in fact, it's more than that. It turns out the volume of the new ellipsoid is less than or equal to e to the minus 1 over 2n times the volume of this one. Now, the good news about this number is it's less than 1. That's the good news. The bad news is it is very close to 1. Actually, shockingly, that is enough to give you a polynomial time result, which actually we're just going to do in a few minutes. So, does this make sense? So, now, compare this volume reduction factor. In CG, what number goes here? Oh, I already gave it away. It's a number. Sorry. So, what expression do you put in CG here? 0.63, right? Which does not degrade. First of all, is a very respectable number, right? It is not 0.99999. That's number 1. Number 2, it does not degrade. Now, the CG method does have a few problems, like, for example, the subroutine that you call to calculate the CG is far harder than solving the original problem. Again, but still, you can see what happens. So this is like a very slim amount. MVE, you get something that's much better. I forget. It's something like 1 minus 1 over n. Is that right? It's in the notes. You just have to look back on a lecture or something. But let's say it's something like that. It degrades with n, MVE, but nothing like an exponential. Okay, so let's look at an example and see how it works. So you can't see it, but there are some sub-level sets of a convex function here. They're not exactly, it's not exactly polyhedral. So I don't know what it is, probably log sum x or something like that. And so you start here, and subgradient, probably gradient in this case, points that direction. And that says that this half circle cannot contain the optimum. I think the optimum is somewhere around here. Okay? That's your localization set, intermediate, is this half circle. And you take that half circle and you cover it with the smallest volume ellipsoid, or smallest area ellipsoid that covers it. And that's this thing. So then you move over here. That's this one. You go to the center, you call subgradient, you get this. This half ellipsoid has now been ruled out, and you have this half ellipsoid, and then you get this thing. And then you jump over here. And I think just looking at these, since this is, I mean, obviously, I reject the idea that there's no problem minimizing convex function in R2. Because you just grid things. I mean, that's a non-problem. But still, the fact that where you have a non-problem, you can sort of visually see that it's going to be slow, it is sort of a hint on these things. And I won't trace through these, but then that's the next 3 steps. And you kind of get the idea. So now let's talk about how do you update an ellipsoid to cover half an ellipsoid. By the way, this is the formula for a neutral cut. So this is how do you cover half ellipsoid with a minimum volume ellipsoid. We also do deep cuts. And in deep cuts, you have to ask, how do you cover a cap, not a half ellipsoid, but something where you cut a fraction off by a minimum volume ellipsoid. There's a formula for that. It's not too bad. So, but let's look at this one where you update the ellipsoid this way. And let me just tell you why. Actually, this is going to be on your homework anyway. So, but I'll just say a little bit about why it's not that big a deal. Let me ask you this. I can affine change of coordinates, and this problem is the same. Okay? If I create an affine change of coordinates for an ellipsoid, when I do an affine change of coordinates, all volumes get multiplied by the determinant, the absolute value of the determinant of the transformation matrix, right? Therefore, minimum volume, I can transform coordinates, minimize the volume, transform back, and I got the answer because everything just got multiplied. Everybody? Okay. So basically, I don't have to consider this general thing. I can transform any half ellipsoid I like to half of the unit sphere, half of the unit ball, just pointing upwards, or whatever, x1 bigger than, or xn bigger than 0. So that makes it simple. Now let's just do this visually, and you have the homework problem. If you have half an ellipsoid, so now you have a half ellipsoid. It's completely circular. It's completely symmetric in the remaining n-1 dimensions. In one dimension, it's got to be positive, but the other one. So that says that the ellipsoid you cover it with has got to actually be symmetric in those dimensions as well. That's a standard thing. We've seen it several times where in convex optimization, if the problem has a symmetry, the solution must. In convex optimization, it has to have the same symmetry. By the way, that is absolutely false for non-convex problems, and you have to be very careful with that. So for convex problems, however, any symmetry in the problem, you can immediately assume that the solution will also be symmetric under that group of symmetries. Okay? So in this case, since you have a half ball that's sticking a cap like this, sticks like that, then it's symmetric in all of these other dimensions, and therefore that means that the P matrix now I think is down to like one, you got one variable or something. I think you got 2 variables to mess with. By the time you're down to 2 variables, it's it's calculus time or whatever. It's not a big deal. It's what you learn calculus for. It's the only thing you learn calculus for. So, okay. So here's the update. For n equals 1, we do know the minimum volume ellipsoid that covers a half ellipsoid. That's easy. That's basically itself, because an ellipsoid is an interval, a half ellipsoid is another interval, and I know the minimum length interval that covers an interval. Okay, so so the minimum volume ellipsoid looks like this. Here's the update. Oh, we're going to, let me just say a little bit about what the data structure is that we're going to use to describe. Lots of ways to describe ellipsoids, by the way, right? Lots of ways. Or at least I know 3, 4. Image of a unit ball, inverse image of a unit ball, quadratic function. I mean, lots of things. But we'll do it this way. We're gonna parameterize it by the center and a matrix P that's positive definite. And in this formulation here, things like, the volume is proportional to, I guess, whatever, something like det P to the, I guess, square root or something. But don't quote me on that. I think it's got to. So the bigger P is, I guess the point is here, roughly speaking, the bigger P is, the bigger the ellipsoid. I get that right? Yeah. Because if P is big, it basically says P inverse is small. And then you can go, Z minus X can get very big before this thing runs up against the limit of 1.
What part of P is big?
Well, yeah, that's vague. Yeah, what does it mean for, so I was being vague. When you say a matrix, a positive definite matrix P is big, when you pin somebody down, it can mean lots of things. It could mean big in determinant, big in diameter, big in the smallest eigenvalue. So I just mean, I'm hand waving.
Okay.
What I'm doing. You could talk about actually which directions it's big in, right? You talk about the so the eigenvalues of P tell you, for example, the condition number P tells you how non-isotropic or anisotropic that ellipsoid is. It tells you, if the condition number is like 2, it says in one direction it's twice as big as it is in some other. If it's 10,000, it says something else, and so on. Okay. All right. But keep in, okay, so let's look at it. Here's the new ellipsoid looks like this, and it's really cool. And I'll give you actually another interpretation of this in a minute. So the new ellipsoid looks like this. The center, of course, it's very interesting. It's a step in the direction PG. I'm going to talk about that. You step not in the direction G, negative G, but in the direction PG. So in a sort of a change of coordinates, you step in a different direction. That's this. Step length is 1 over n plus 1. And the new ellipsoid looks like this. And I want to dissect the different parts. Okay, remember P big, in matrix sense, roughly corresponds to E big. So let's talk about the different parts. Let's forget the scaling, and let's focus on this. This, by the way, what is this matrix here? What's the rank of that guy?
1.
1. Rank 1. It's an outer product. It's like PG times the transpose, okay, with a constant in front. This is actually, that's a rank 1 down date. In other words, you take a positive definite matrix, and you subtract a rank 1 thing. I mean, now you can't subtract, I mean, this thing is carefully, well, by definition, this cannot be positive. This is, again, positive definite. But you know what that means? If I ask you about, suppose, let's take the ellipsoid defined by P, and then the ellipsoid defined by that. What can you say about the second ellipsoid? What happened to all what can you say about all the eigenvalues of that matrix, for example, compared to the eigenvalues of that matrix? You can guess, but you don't have to absolutely know. You can just guess.
Must have gotten smaller. Right?
What?
Must have gotten smaller.
Yeah, they must have gotten, well, that's true. They all got smaller. This matrix is less than or equal to P in the matrix sense. Because it shrunk. Actually, it only shrunk only in one direction did it shrink. It actually shrunk in the direction PG or whatever this is. G tilde is the normalized thing. It only shrunk in one direction. Okay? But it got smaller. Therefore, that's the good part. This is the good part where P gets smaller. Then you multiply by this. And what happens to what happens to the ellipsoid when this happens? You increase it. So basically, I mean, I don't know if people have seen this in like, sort of Kalman filtering or this kind of stuff. I mean, basically what happens is you have this, again, this is only if you've had these classes. Just if you haven't, don't worry about this. You'd have 2 steps, right? What happens is you think of first you take a measurement. Does anyone here have you seen these guys? Okay, so you take a measurement, and based on the measurement, your estimate of the current state, gets better. So your covariance matrix goes down. Well, it had to. You just got some information, and if you know how to process the information correctly, how could your estimate get worse? Okay, so your error covariance matrix goes down. Okay. Then the next thing that happens in sort of like a Kalman filter or this thing is you multiply, you propagate it forward by the dynamics and add some unknown process noise. And what happens then is in that step, that's the dynamics update, your ignorance increases. And the hope is when you're running this whole thing after many steps is that the amount of increases in ignorance, in that case measured by a covariance matrix, right, that is overwhelmed by the amount of decreases in ignorance that come every time you take a measurement. So that's what's happening is you have a vehicle or something you're tracking. It's being disturbed by something you don't know. That's a process that's leading to increased ignorance at each step, but you get noisy measurements of it. And that's a process which, if you process those measurements correctly, lead to decreasing ignorance. And so this is the same thing. So that's the decrease. And the decrease came from essentially a kind of a measurement. I mean, I don't, if you want to call this a measurement, well, you can. That's a measurement. And then that's sort of that's actually your slop. So that's how this works. And I can actually, I want to give another interpretation of this, because, I mean, anyway, you're going to prove this formula. So here's what I'm going to do. I'm going to write down an interpretation of that, which, actually, once you see this interpretation, you don't need to know anything else. So it's this. Let me see if I can get I just want to interpret the step. Okay, so here's the way it goes. You have an ellipsoid like this, and here's your point. And you get a subgradient. And let's say the subgradient points this direction. Okay? That's the subgradient. Now, suppose you were doing a subgradient method. Where would you step in a subgradient method? You'd step somewhere along here. Now, where depends on your step length at that step. And your step length could be as stupid as 1 over k. Right? So you'd step in this direction. Let's actually see where you step here. Where do you step here? That's the question. And we don't have to, I mean, I'll just draw it geometrically. It turns out what you do is you go in the direction, you solve actually a problem. This direction that you step in solves roughly this problem. Here's how you get the direction. You minimize sort of G transpose V, where V is a direction, subject to V in your ellipsoid. Okay? So you go as far as you can in this direction in this ellipsoid. And in that case, I'm going to try to draw it. I'll probably get it all wrong. But anyway, it looks something like that, right? And so it might be here. So in fact, this is the direction. If that's G, that's minus PG. Roughly. I mean, forget the scale factor. This guy down here is like minus G. And so what you see is that, in fact, you can think of it as it's a distorted, it's like Newton's method. It's exactly like Newton's method. Instead of going in a negative subgradient, you're twisting it by a positive definite matrix. Okay? This makes sense? And you can check that that PG is sort of this direction here. And there's a beautiful way to interpret it, which is absolutely amazing. It's this. And it's in change of coordinates. So change of coordinates interpretation goes like this. Here's your ellipsoid at step n, or k, or whatever. What do they call it? It doesn't matter. Here's your ellipsoid at some step. And what this says is, the ellipsoid tells you your ignorance, right? If it's round, it says you're equally ignorant in all directions, right? If it's this like little pencil-like things, it means that you have very good knowledge of the solution in some directions and very poor in others, right? So what you do is you say, no, I don't, you change coordinates. And by the way, you change coordinates in the original thing by multiplying by p to the half. So you use coordinates z equals p to the half times x. When you change coordinates to make your ignorance round, to make it isotropic. So you're equally ignorant in all directions. You change coordinates. Now when you change coordinates, you get a transformed g. Let's call that g, I don't know, g, so g had been pointing in some direction. Well, it doesn't matter. This is your new, I'm going to call it g bar. That's g, but transformed, in fact, by this p to the 1/2 or whatever. Okay? Now in this case, the question would be, which way to step? And so the correct step in a situation where your ignorance is isotropic, so you're equally ignorant in all directions, the correct step is to go minus g bar, and it's even funnier than that. It's basically divided by like n plus 1. This constant step length, 1 over n plus 1. Period. That's it. That's it. That's what the ellipsoid method is. So, and in fact, the original discussion of ellipsoid method, which was, I guess, by Shore and you had this name. In fact, it had a very long name. I'm trying to remember because it's really funny when translated in English. It's subgradient method with space dilation in the direction of the gradient. So this is space dilation because when you're changing coordinates, and by the way, the dilation is only in one direction at each step, because when you do just a rank 1 update, you're actually just scrunching space. Actually, you're expanding it, you shrink the ellipsoid, and that has the equivalent in the change of coordinates of dilating space in the direction of the subgradient. So when you look, if you were to go to Google or look at some of these early books from the 60s and 70s, Russian books, they would be, some of which, by the way, are actually in English and are superb books. You'd have a long distance, instead of ellipsoid method, you'd hear ellipsoid method with space dilation in the direction of the gradient, and various other things translated like that. So this makes sense? Then the thing you don't do in an ellipsoid method, in the subgradient method that you do in ellipsoid is once you step this way, this ellipsoid gets shrunk. You learn about stuff in this direction, so you shrink a little bit. And then you pull it apart. You do a change of coordinates to rebalance or isotropize your ignorance. That's definitely not a word in any language. Make isotropic. Okay, so this makes sense? So this is the picture. So in some sense, what's funny about this is it's a little bit like Newton's method, the story, because if someone says, what's Newton's method? And you can write down some formulas and stuff, and they'd say, well, why would anyone want to do that? And you can blabber on and on. But if someone says, yeah, but what's the idea of Newton's method? You could say, well, look, the idea is that the gradient method, although it's the first thing you could think of, it's greedy, and it might look like a good idea to go downhill the fastest way that way, but it might turn out that you should really be going about 45 degrees over that way, or more commonly, 89 degrees that way. And someone saying, why? And that's because, you draw a valley and all that. Okay, and then you say, all right, Newton's method is basically the gradient method applied after a change of coordinates makes the curvature locally isotropic. That's what it is. So the one case when greedy is good is when your ignorance or your function has equal curvature in all directions. And this is just kind of the subgradient method with this. In fact, people have a very beautiful term for these things called variable metric. So the metric tells you about the topology of the space, and so you would talk about Newton's method as a variable metric method, a variable metric gradient method. And in fact, you talk about ellipsoid method as a variable metric subgradient method. It has this other interpretation and so on. Okay. Now the stopping criterion is pretty simple. And the way that the stopping criterion, let me just draw that over here. And then I have to tell you something embarrassing about the stopping criterion. So here's your current ignorance level. And suppose I give you a subgradient like that. Well, if you were going to do another step, you'd cover this with an ellipsoid, and that would be your next point. And actually what you'd do, now you know geometrically what you'd do. You would go you'd solve the LP of going as far as you can in that direction here. And in fact, that would give you to this point, right? And so in fact, your next step direction, now you know how to construct it, is here. And then the step length is somewhere along here, given by some formula. But you're not going to do that. You're going to terminate. And what you do is you stop, you send a signal to this process, and you say, done, time's over. Give me a lower bound. Give me your current point. That's this thing. And they'd say, please give me a lower bound on how far you are from optimal. Well, what you do is this. Of course you have this. This is just your basic formula for, everything's based on this. Everything is based on this formula. It's the definition of a subgradient. Everything's based on that. So what you do is this. X star is in this ellipsoid. That's the whole point of the ellipsoid, right? The ellipsoid is a localization region. Therefore, this thing has to be bigger than or equal to the infimum of this linear affine function here over the ellipsoid, like that. Just has to be. You can just analytically work this out. I mean, what the worst thing is. In fact, the worst thing is, in fact, literally what you're doing is you're solving this formula here. You're calculating this point. And then when you put that back in, this just has an analytical formula. It's this. And so it's absolutely beautiful. Square root of G transpose PG is actually a guaranteed suboptimality bound. And it's absolutely beautiful. Do you know what it is in this in the transform space? It's this. It's the norm of the subgradient in the current coordinate system. Because if you change coordinates. So, and I mean, this kind of just makes beautiful sense, right? And that's a guaranteed suboptimality. And in fact, it makes sense because if someone walks up to you on the street and you say, listen, consider a unit ball. So that's your kind of your standard ignorance set. You say, I have a unit ball. I evaluated the subgradient at the origin of a function, and I got this. I know the minimum is somewhere in the unit ball. How far could I be off? You get this. Except it's just the norm. It's just the norm of G. That's how far you are off. Okay, so there's a beautiful stopping criterion, especially because, in fact, I think you calculate that as a side calculation anywhere, somewhere here. Yeah, so you have to calculate this anyway. You calculate it right here. So basically, you calculate this. If it's less than a threshold, you're out. Otherwise, you update. Okay, now, and I do have to tell you one thing about this. Well, here's the ellipsoid algorithm now. I'll show you the whole algorithm. Now I'll tell you, I have to admit something about it. Okay, so you start with an ellipsoid containing x star. You know, typically the same way in an ACCPM might be some box or something. It's, you know, this might typically be a ball of radius capital R. That'd be very common. Okay, here's what you do is you evaluate a gradient. If the gradient in the scaled norm is less than epsilon, you return x, and that's absolutely certified. I mean, there's nothing fuzzy about that at all. Otherwise, you update the ellipsoid like this and you repeat. That's the ellipsoid method, and now I have to tell you the truth. Yeah, it's not the truth. It's not. We're not lying. It is not known, as far as I know, and I spent last summer, I spent like a week with all the people from Moscow and Kiev in the 60s. They were all there. Enough of them spoke English, so everything was cool. There was a lot of vodka, though, so that was on the other side. But it's not clear. Anyway, they claim the following. There is no proof that the exit criterion 2 will be, no general proof that the exit criterion 2 will actually be satisfied. So, I mean, there's no reason to believe it. So the only actual stopping criterion is the one that comes from the complexity theory. Actual means, you know, you can absolutely prove it will be reached and blah, blah, blah. However, this works invariably in practice. So, okay. I think we already talked about this, right? There you go. So we already, okay. So here's an example of ellipsoid method. This is our now famous ellipsoid method. And, well, you can kind of look and see how it's working. Each step is, by the way, I think order n, is it n squared or something like that? Actually, let's go back and see what the ellipsoid step is. Yeah, it's order. It looks like to me like it's order n squared. It's n squared. I'm seeing n squared. Everybody else seeing n squared here for the ellipsoid? The numerical update, I think, is n squared. The reason it's n squared is, I don't know. Here, you have to write all the entries of p out. So there's n squared right there. And other than that, I don't see anything fancy except I'm seeing matrix vector multiplies. So it's order n squared. So this just shows kind of how it works slowly and badly and so on. This is the lower bound, which is indeed getting better. So I think what we'll do is we'll quit here, and we'll sort of finish this up next time, which will be next Thursday.